Okay, maybe should I go on? So hello everybody. Let me just say a word for Dr. Chen and Dr. Ray Zhang, who's gone before. All very nice persons. They won't say that about themselves, but you will be. If I can do PhD again, I'd be very happy to join their groups if they would take me. I guess I have 15 minutes starting now, or okay, wonderful. So thanks to Dr. Yuan and Associate for arranging this event, and thank you all for coming. My name is Alex Wong. I'm an assistant professor in this department, and I work on hardware electromagnetics. I just want to check, are you all seeing this slide? So maybe you can let me start the presentation, and it will be helpful if maybe one of you can type in the comments if you can see and hear just fine. Oh, I have some messages. Wonderful, thank you, Hobo and Ziting. I think we can begin. So I want to begin with a department video that's just come out. So yes, Yishan, my video at long last has come out, and this tells you a little bit about my group. Ooh, what happened? My name is Alex Wong, and I am an assistant professor in electrical engineering at the City University of Hong Kong since 2018. My research lies in the area of applied electromagnetics. Electromagnetic waves, or EM waves, come in a form of visible light as well as frequencies that are invisible to the human eye. Electromagnetic waves find important applications in 5G wireless communication, IoT networks, wireless power charging, medical imaging, and scientific microscopy, among other applications. In recent years, I've performed research on the metasurface, which is an artificial surface that can absorb, transmit, and redirect electromagnetic waves with strong flexibility. These surfaces give unprecedented functions and performances to antennas and microscopes. In our group, we have recently proposed a surface which bends an electromagnetic wave with very high efficiency across a bandwidth, which is very large, and yet have much larger feature sizes compared to existing metasurfaces. This makes it very easy to fabricate for millimeter wave frequencies and used in automotive radar and potentially in future 6 to 8G communication systems. In another branch of work, we have used a new Huygens box concept to create a traveling electromagnetic wave inside a metal box. Essentially, the EM wave flows like water in a river from one side to the other side of the box without reflecting off the metal boundaries. We then use this box to build a steerable directive antenna with potentially less than 10% of the components and cost of a conventional antenna system. The antenna system is currently in the testing stage. Such an antenna system will find very strong application in future wireless communication systems. For me, research is a team endeavor, and I'm fortunate to work with a group of motivated students to bring our innovations toward real applications. It's especially pleasing to learn alongside my students, to give them the guidance and support they need, and ultimately watch them grow as professionals ready for careers in the academia or the industry. Beside my close-knit group of students and postdocs, the world-class facilities at the City University of Hong Kong's Stay-Key Laboratory of Terahertz and Millimeter Waves has helped me tremendously in my research. I am also grateful for the government and industry sponsors in the Department of Electrical Engineering for helping me set up my microwave and optical lab facilities. The City University of Hong Kong is an exciting and enthusiastic place for advancing scientific research. I'm grateful for launching my career here. I'm always looking for prospective students who are motivated, hardworking, and wish to contribute to the forefront of science and technology. Please contact us if you're interested. Let me come back to the presentation. As we were saying, I think I'm very glad to begin exciting research groups here, and you've heard a little bit of the research directions. I'm sorry, the Zoom setup is a bit awkward here. Okay, I will just go on, but if anything goes wrong with the Zoom presentation, please let me know, because it looks like I'm not seeing our students and I'm not getting some of the Zoom functions I normally get. But in any case, I want to say the research will not be possible without many members of the research team. These are current group members. Some of them will leave the group after the summer, and then these are some collaborators. But really, the heart of the research is really in the students that are doing the research, and that's why I'm here. And as we have said in the video, to continue the exciting research direction, I really will appreciate having good prospective students to join the team. So that's where you come in. And I hope some of you will find my research interesting and will thereby consider joining my group. So the video has introduced my research and two major branches, which I will talk a little bit more about in the next few minutes. But as a whole, my research area is primarily in metasurfaces, and but also with another branch in super resolution. So obtaining resolution that is physically either impossible or non-trivial, but doing so using creative ideas, creative methods with electromagnetic waves. And these encompasses both passive and active metasurface. Active means you put in some power to achieve a certain function. And the main application regimes are in imaging and communication. So looking at things, making clear things, and communicating between different entities. For those of you who do not know, the metasurface, I'm sorry. 遲啲揾返你做緊 presentation. Bye-bye. Okay. So the metasurface is basically, for those who don't know, the metasurface is a surface that you can design. Kind of like this funny mirror if you walk into a park that maybe you are short and you are a bit fat, and the mirror can make you look tall and slim and handsome. So the metasurface is a flat surface, but it changes the electromagnetic waves like how the mirror changes the light waves, except more powerful. So you can tune the strength of the wave, you can tune the phase when it reflects or transmits, you can tune the direction of the electric field, and you can tune the direction where the energy is going. By tuning these many physical parameters, you use your knowledge in physics to basically make a flat lens that can do almost anything to the wave that you want. And you can see how that's very useful for microscopes, for telescopes, for antennas, for many things that we use in communication and imaging systems. These are some early examples of how to design near field and far field metasurfaces, including this very early work from myself when I was a student. And more recent examples of how you can integrate a metasurface with an antenna or put a metasurface above an antenna to make antennas and intelligent surfaces for 5G and 6G communications and beyond. I myself have some projects in this area, both as academic projects and as industry collaborations with international companies on antennas and telecommunication. So one of the main projects I work on is called the discretization. Basically, we look at how to build a metasurface like a puzzle. So many people build a metasurface with very small puzzle pieces. Each of the puzzle pieces is a lot smaller than the wavelength, but it has some drawbacks. For example, when you make those very small elements, it can be very hard to make or very expensive to make. And small changes in the frequency, in the angle of arrival of the wave, can change the characteristic of your surface's response dramatically. So it's not very robust. In our group, we find that actually making things with larger cells, it requires a different design mechanism, which we have mastered, and we're now publishing our results on this topic. But this exercise helps us understand better about how using the large puzzle pieces, the large elements, can affect the metasurface performance. And in some cases, it can both simplify the metasurface construction and improve its performance, like make it absorb less power and make it work for a wider bandwidth or wider angles of arrival. So there are various advantages to this. In a very simple work from a few years back and published quite well, we made basically a surface that bends the wave completely. Instead of going to the direction where the reflected angle is the same as the incident angle, we redirect it to some weird arbitrary angle. So the idea is that if you can redirect the wave any way you want, then you can build a lens, then you can do many other things. We've done it at a frequency of 24 gigahertz, where basically the 5G frequency in Hong Kong, the higher band that will come out a little bit later is around this range, or maybe just a little bit higher. So this is like the frequency range are things we're looking at for the later 5G or approaching future generations of communication. The kinds of work I have done here and my students would do in my group involve the conceptual design and the theory. And then we investigate the electromagnetic response of a structure like this, where purple is a dielectric material. The yellow color is copper, is the metal material. We program this information into a commercial electromagnetic simulation tool, and we observe the performance. This is the performance, this is the reflection corresponding to a single element. And then when you have two elements, actually the wave will come in like this and will reflect like this. You can see the reflection wave is very pure in one direction. So this is a very successful design. And then we simulate also the finite structure to find that basically very good reflection and very little reflection in the normal direction results over a very wide bandwidth when you sweep from 22 to 28.5 gigahertz. So it's a very successful results. If you're in my group, you will then go on to test the device in an experimental chamber. This is a chamber where the wave comes in over here, and then the receiver wave will be reflected, will be on a rotating stage. In the real experiment, there will be a cable connecting from here to the measurement device. So you will be able to, you will see you'll collect the scattering or reflection results. This is sort of the metasurface, and this is a zoom in of that. In the interest of time, I cannot say too much more, but that we've moved beyond that work. A current student in my group now has made a transmission surface where the original surface is discretized to 20 elements. We make just 3 elements. So each element is about 6 by 6 times larger than the original element. So you can see this is the original structure. It's got 3 layers, and this is a new structure. It's also got 3 layers, but each layer is a lot simplified from the previous one. But despite that, we find that the metasurface performance actually improves. So that's one of the works. There are many other works on different variations. This is a dielectric Huygens metasurface, which we are printing with a printer in our university. And we also do some active works, which looks like I would not have time to talk about. But it basically has to do with making a wave inside the box, for which you've seen some of this in the video. You can make a wave and it travels inside the box and it gets absorbed at the end of the box and doesn't reflect. And using this, you can do things like cloaking, hiding something. And more recently, we've demonstrated, or in simulation anyway, an antenna beam coming out of this box. So there's the box and there's the antenna beam coming out. Fabrication is a bit further than this. We've actually made the box. We're in the process of testing it out. Some of the new project directions are listed here, including metasurfaces that are broadband and true time delay, metasurfaces whose properties change with time, and metasurfaces that read information from the environment or responses to the environment based on machine learning. Again, applications include communication, imaging for medical and biomedical purposes, and intelligent surfaces in a room. So again, all this is not possible unless I have very good students who work with me, who are intelligent, passionate, curious, hardworking, and conscientious, and have relevant courses of preparation in these areas. Antennas, microwave, electromagnetics, signals, and signal processing. So if you're interested, we welcome you to join my group. Here's my email and here's my website that you can find more information about me and my group. And you are very, very free to, please feel free to contact me for more information. So let me stop here and invite either your question or maybe Dr. Yuan will kick me off because I'm a bit over time. So I thank you for your attention.
So Alex, you are the last one in the morning session, so we have some time.
Oh, okay. Well, thanks. I don't know. Maybe there aren't questions. Maybe most of you are interested. Maybe I will go back. I think many of you are interested in things like machine learning and well, the softer side of things. I think in my group, if you do decide to consider, we have projects in this area where we do look for example, machine learning and algorithm experts to apply it in a more physical environment. So I get a question from the chat. What is the Huygens box? Okay, so to simply put, the Huygens box is, and maybe I use this picture, is an environment where you put in electric and magnetic currents to change the boundary conditions for electromagnetic waves. What it effectively does is it separates inside from the outside. So in this picture, the outside can be a wave coming in the north, toward the northeast, but inside I can tweak it so that I turn it into a wave going from to the northwest. So the Huygens box is a box where I close it off and I tune the inside of the box completely free of whatever's outside. Or I can do the reverse, tune the outside of the box completely free of what is on the inside. This is what the cloak is. So there's a wave coming in. I have some metal object or dielectric object here. It can be a square. It can be a Mickey Mouse hiding inside. But as long as I know what wave is coming in, then I can tune the box so that the wave coming in is canceled here, so that whatever's inside will not be scattering the waves from the outside. And so in the outside, I put my camera, I put my antenna here. I cannot detect if something is in here. So this is a fun application. Oh, I'm sorry, I didn't modify this. This has been published. You can read the paper. You can find a link from my website. But the idea is that I can separate outside and inside of the region, and I can do some cool things, like what I show later on with the antenna. I can make the wave travel, like what I show, water inside a river. I tried to play this, but there's some error with the codec. But I make some holes on the top of the box, and a very nice wave leaks out on the top. So this is very useful because there are other ways of doing this with current antenna technology, but they require the number of elements that's proportional to the area. in what I do, I require the number of elements that's proportional to the perimeter. So I save many, many elements, and I save a lot of money while sending out the same wave. I hope that answers your question, but you're free to ask more or more detailed if you wish. Okay, thanks. Very good question. As that is not a conventional terminology. We started this initiative a few years back, and my student is about to push out some more papers, but it's taking some time. So I give maybe a little bit more time for further questions, if any. Okay, if there's nothing else, maybe I stop my sharing and I return the time to Dr. Yuan.
No, I think that's all for the morning session, and see you at 2 o'clock.
Okay, dismissed and lunchtime.
Yeah.
Thanks for attending. I hope you find the right supervisor through this event. So goodbye.